Hello. Okay. Good afternoon, everyone. Apologize for being late. So let's get started. So don't forget we have a quiz by this Friday, and next week will be the spring break. So no quiz. You don't need to invest any time in homework, and of course, if you would like to do that, you're more than welcome to do that. But if you can spend some time taking a look at our newly released homework and make sure you plan ahead. Right? Okay, so let us continue with the joint probability density function for discrete random variables. Right. So in last lecture we talked about the motivation. So in many cases, in many scenarios, we want to look at what is the behaviors or what is the relationship between multiple random variables, right? Not just one random variable. For example, you want to take an experimental process for multiple times and look at all the outcomes altogether. Right? Or if you want, if you invest on stock market, you probably purchase the 10 stocks rather than one. Right? You want to look at overall how this 10 stocks, their performance, their relationship, and so on. Right? So to study the relationship of multiple random variables, we want to define this joint probability density function. So we start talking about discrete random variables. See, I got two random variables. Right? So for a single random variable, see, x1, right? We know from our previous discussion, the PMF or PDF is defined as the probability. I'm not gonna use another notation. The PDF for x1 actually is the probability of the event that x1 takes the value a, right? And this is a special event which includes all the samples in the sample space such that the random variable's value on this sample is a, right? We have repeatedly review this concept again and again, right? So it's just that it defines a particular type of event. So now, when we look at, maybe let's write down the PDF for another random variable. So if I look at x2, right, I only look at the probability density function for x2. This function is defined as the probability that the event x2 takes a happens, right? So this is about a single random variable and its definition for PDF or PMF. Right? So now, when we come to the joint probability density, we usually denote the joint density as like fx1, x2, like x1 comma x2 in subscript. Say I got A and B, right? So what's the definition of this joint PDF for discrete random variables x1, x2? Anyone? How do we extend the single probability density function or the probability density function for single random variables to joint PDF? Any thought? You got something to say? Yeah. No, it's not. Right now, we are not talking about continuous random variable. When we talk about continuous random variable, we're gonna look into some integration and those kind of stuff, right? Right now, x1 and x2 are both discrete random variables. How do we define their joint probability density function or joint probability mass function? They're interchangeable. Are you talking about how to calculate that? Yeah, I mean, here the definition is just do a joint probability of the two events, right? So you see, for a single random variable x1, the PDF is just the probability of the event x1 takes some value, right? And for another single random variable x2, the PDF is defined as the probability x2 takes some particular value, right? So now if you want to look at their joint probability density, we just need to look at what's the joint probability of these two events happen. Right? That's the definition. Right? If we write it down, it is the probability that x1 takes A and x2 takes B, right? So you see, two events, you do the intersection, that means like both A and B happens, right? So that's the definition. Just keep it in mind because this is really fundamental and important, and you should expect to know it by default. Right? So, and for convenience, right? People usually like won't put this big brackets of outside. So when you read the definition of the joint density function in textbooks, they will just abbreviate written like x1 equals to A, comma, x2 equals B, right? So the underlying meaning is just means like, okay, it's just an intersection of two events. One event is represented by x equals A. The other event represented by x2 equals B. Does it make sense? Right? So, and if you look at this joint PDF, right, for two discrete random variables, you know, okay, x1, x2, x1 can take a number of values, right? So x1 might be a1 to am, right? x2 may take another set of values like b1 to bn, right? So then you see this joint density function essentially can be represented by a table, right? So you can imagine when we look at this function, we can actually draw a table, right? So maybe row represents x1 and the columns represent x2, and each row represents every value x1 can take, and each column represents each value x2 can take, right? The entry, say 0.1 here, just represents the value of the PDF, the joint PDF. Any question? Okay, great. So in the last lecture, we gave some simple example to show how do we represent this joint probability density function, and how do we marginalize out the probability density function from the joint density function, right? So let's look at a second example to help us better review this concept and better understand the definition, right? So we got an experiment where we flip two fair coins. By fair it means like, okay, you have the equal chance to see half. You have the equal chance to see heads up and tail up, and you flip two fair coins. That means like your sample space will be what? What is the outcome for each experiment? Will be either like, will be two outcomes, right? So every outcome, every sample in the sample space will be something like 1, 0, 0, 1, 0, 0, 1, 1, right? That's the sample space. Okay. Of course, here, 1 represents heads, and 0 represents tails. Okay. Maybe I should write more clearly. Head, tail. Okay. So now we define 2 random variables. The big H, the capital H, is the total number of heads. Okay. And B, and big B, capital B, is the binary number that the 2 coins represents. So if you look at the sample space, right? If you look at the sample space, right? You see this sample 1, 1. What's the value of H? Maps to what value in H and what value in B? Yes, exactly, right? Remember, H and B are random variables, right? They're just mapping from the sample space to some real number, right? So the sample space contains four elements, right? 1, 1, 1, 0, 0, 1, 0, 0, right? That's all possible outcomes of your experiment, right? So for 1, 1, H is the total number of heads. Total number of heads is 2, right? And B is the binary number that is represented by the 2 coins. So that means 1, 1 means a binary number 1, 1, right? The binary number 1, 1 actually is 3. Does it make sense? Right. 1, 1 is the binary number, and if you convert it to decimal number is 3, right? Okay, so how about 1, 0? What's the corresponding value of H and B? Yes, exactly, right? So 1, 0, that means that you only see 1 head, right? And 1, 0, this binary number, when you convert it to a decimal number, it is 2, right? So how about 0, 1? H will be 1, right? We still have 1 head, right? And the binary number now is 0, 1, right? So the decimal number is 1, right? And finally, for 0, 0, the value of H will be 0, right? Because no heads. Same. And for value of B is 0 as well, right? Because if you look at the binary number 0, 0, it's nothing but 0. Right? Any question? Okay, great. So now let us try to figure out what is the PDF, joint PDF for H and B. Okay. So as we mentioned, the joint PDF is the joint probability of two events, right? One event is H takes a particular value. The other event is B takes a particular value, right? So now let's fill the table, right? Because this joint density, probability density is represented by a table. So this one. So this is H, this is B. So H, you can take value 0, 1, 2, right? And B, you can take 4 possible values, 0, 1, 2, 3, right? So this is a 3 by 4 table. Let us just try to fill the numbers. So first, what is the entry at 0, 0? Namely, the joint density function at 0, 0. What's that probability? You just look at this represent the event that your H takes the value 0 and B takes the value 0 as well, right? So the intersection of these two events, what kind of elements, what are the set of outcomes does it include? Yeah, there's only one outcome, right? Which can be included in this joint event, right? There's no other outcome which can also make H is 0 and also B is 0, right? So there's only one outcome. So what's the probability you see this outcome? It's a fair coin, right? Yeah, 1/4, right? Because you have the equal chance to see every possible outcome. Right? That's called fair coins. Right? So then we get the value for our first entry. Right? So how about the second one? H is 0 and B is 1. What's that? This is defined as the joint probability of H is 0 and B equals to 1. Let's see what set of outcomes it includes. Do we have an outcome which can give H 0, B 1? Do we? Yes. So that means that event is actually an empty set, right? Empty set, the probability is always 0. So we got our second entry, right? So about third one, H is 0 and B equals to 2. Probability of the event that H is 0 and B equals to 2. 0, right? No event, no outcome will give you H is 0, but B is also 2, right? So actually, You can see that because as long as B is non-zero, that means at least you will have one head, right? But when H is zero, that means absolutely no ones in outcome. So that means not only do we have the density function for H0, B2 as 0, but also for H0, B3, right? Because when B is non-zero, you must have at least one head, right? But it is contradicts to that H is 0, right? No heads are observed. Does it make sense? Okay, so I mean, we just keep doing this, right? So how about the PDF at H is 1 and B is 0? What's this? What's the value for this function, density function value? Yes, right? Because if you look at the outcomes, right, there is not any outcome that can give you H as 1 and B as 0. The reason is simple because H is 1 means that there is one head, right? And then B cannot be 0. If you put a digit 1 to a binary sequence, right, this binary number will always be bigger than 0. Does it make sense? Right? So that's why this guy must be 0. Silly Siri. I don't know why it cannot be silent. Okay. So similarly, if you look at PDF at H is 2 and B is 0. What's the value? 0 as well, right? Because H is 2 means that you got two heads, right? You got two heads. How is it possible when you have a binary number contains two ones and the binary number is still 0? It's not possible, right? If you look at the mapping here, you also won't find any outcome will give you H is 2 and B is 0, right? So this guy must be 0 as well. Okay, so now first row and the first columns are done, right? So the remaining, let's just take a quick look. Right? So what about H is 1, B is 1? We know it's a probability that H takes 1, and meanwhile B takes 1. Which outcome of this joint event, what set of outcomes are included in this joint event? Any thought? This one, right? If you just look at this mapping table, right? We know that, okay, there's only one outcome, 0, 1, which gives H equals to 1 and B equals to 1, right? So what's the probability? 1 to 1, right? It's a fair call. Okay, so what is the density function at 1 and 2? 0. Yeah, we just take a look at if we can find any outcome that gives H equals to 1, but B equals to 2, right? No such outcome. Right? Yes. Oh, Oh, yeah. You're right. Yeah. Okay, thanks for pointing out. Yeah, we actually find one outcome. This one is 0, which gives you H is 1, but B is 0. Why? Because the binary sequence for this is a 1, 0, right? The number is 2. Yeah. So what's the probability? Yeah, 1/4. Okay. So how about H is 1 and B is 3? Do we have any outcome that give this? No, right? You can't find any pair of the H and B, which one is 1 and the other is 3, right? So this guy will be 0. And we just keep looking at this, right? So it's a little bit tedious, but it's good for us to practice our understanding. So how about H is 2 and B is 1? Do we have any outcome that gives H2 and B as 1? No, right? So this guy will be 0. And how about H is 2 and B is 2? It's not possible, right? H is 2 means that you got 2 heads, right? As long as you got 2 heads, B must be 3. So this part is 0. Okay, the last one. What's the PDF when you got H is 2 and B is 3? Which outcome gives this? 1, 1, right? You got 2 heads and you put them as a binary sequence is 1, 1, which gives 3. Right? So what's the probability? 1/4, right? Perfect. Right? That's it. We have finished calculating our joint PDF function for H and B. So now let's just keep this table aside. Let us look at the PDF for each single random variable. So what is the PDF for H only? So for H only, we can also take a look at here, right? H is 0, 1, 2, right? So this is a PDF. Okay. So this guy is the probability that H takes a particular value, right? So now, when H is 0, what's the probability? Or what is the PDF for H? Again, if we just take a look at H, right? And you need to look at this event, H equals to 0, right? Includes how many? Y? Or is, yeah, there's only one outcome, which gives H 0, right? So the probability of this event is 1/4, right? Okay. So how about H equals to 1? Why it is 1/2? Yes, exactly, right? So here we need to be a little bit more careful because this, when we calculate the probability that H takes 1, this event actually includes 2 outcomes, right? 1, 0 and 0, 1. They both give 1 heads in total, right? 1 head in total. So the probability will be 1/2, right? So what's the PDF at 2? 1/4, right? Actually, we don't need to calculate the probability. We just subtract 1 by 1/4 and 1/2. You get the PDF value for the remaining the remaining PDF value. Okay. Any questions so far? Okay, so let us also take a look at the PDF for B. So B has 4 possible values. Zero, 1, 2, 3. I'm gonna make it B equals to some value, right? 0, 1, 2, 3. Okay. Oh, sorry. 0, 1, 2, 3. Okay, so what is the PDF of B at 0? What's the event of B equals to 0? It's just this one, right? There is only one outcome, 0, 0, that gives B 0. So what's the probability? 1/4, right? Okay. So what is the PDF B at 1? 1/4, right? You see, there's only one outcome, 0, 1 gives PDF B is 1, right? 1/4. And what is PDF at 2? 1/4, right? And last one is 1/4. Okay, so now we just use the problem itself and the definition to calculate the joint PDF and the marginal PDF for each single variable, right? So now let us just check whether they kind of match each other. Right? So as we mentioned, if we want to get a marginal probability for marginal probability density function for one variable, you're going to sum over the joint density function over another variable, right? So that means if I want to calculate the PDF for H only, I'm going to sum the joint density over B. That means on this table, I'm going to sum over columns to get B, right? To get H. Because I'm going to look at when we fix H and how the B varies and adds up all the joint density values together to get the marginal density value for H. Okay. So if you sum over every row, what do you get? No, sum over all the columns, right? So for the first row, if you sum all the columns, the value is 1/4, right? The second one is what? Half. Okay. And the third one is what? 1/4, right? So you see, it is exactly the same as we computed. Right? Does it make sense? And if you look at the marginalization over H to get the PDF for B only, that means we're gonna sum over rows. We're gonna look at, then we can get the PDF for B at every possible value that B can take. So if we sum over rows for every column, what do we get? Any thought? What's the summation for the first column? 1/4, right? How about second? Third? Fourth? Yeah, that is exactly right, right? So you see that when we marginalize out H, right, we get the PDF for B only. This exactly is the same as we computed for the margin for the PDF of B, right? So you can see that, okay, that verifies our calculation is correct. Any questions so far? Okay, so now given a joint probability density function, we further define a so-called conditional probability density function. So what is conditional probability density function? I mean, it is usually abbreviated as conditional probability. It is denoted as this way, right? So the conditional probability of X condition on Y when Y takes B and X takes A is defined as the joint density function of X and Y at A and B divided by the marginal density of Y at B. So you see that we got a conditional part, Y, right? And to calculate the conditional probability, we need to calculate a ratio, right? And the numerator will be the joint density function value. And the denominator will be the marginal density function value for the conditional part. That's the definition. Right? It is often written in this form, which might be more easier, which might be easier or more intuitive to read, right? So it represents the probability that X equals to A given Y equals to B. Right? That is the probability that the event, given that the event Y equals to B happens, the event X equals to A happens. So this is the definition of the conditional probability. Any question? Okay, let's rest for 5 minutes and then continue. Okay. So let's continue. So we just define the conditional probability, right? So it's just a ratio. You normalize the joint density by one marginal density, you get the conditional probability. Right? So, so again, I mean this kind of formula is nothing else. It's just the definition, and we'll need to use this formula to calculate a lot of things. That's why we need to practice. So let us look at this binary communication example again. Right? So remember, this talk about, okay, under a noisy wireless environment, when I send some message, what will happen, right? It is possible that your message will be corrupted, right? And we consider just to send one bit information. And there's some chance your bit will get flipped, right? So if we denote S as the sending bit, R is the received bit, right? So here we give the joint density function, right? F S R, right? So you see this is a table. So from the table, you can see, okay, the chance that your sending bit is 0 and received bit is also 0, is 0.45. And the chance that your sending bit and is a 1 and the received bit is also 1, 0.41, right? But you have some like smaller chance that your sending bit is flipped when it is received, right? So now we would like to use the definition we just introduced to calculate the conditional probability. So what is the conditional probability that R given S, where R takes 1 and S takes 1? From the definition, this is the probability that R takes 1 given S takes 1, right? Right, this is just the definition here. And according to the definition, this is a ratio. The numerator will be the joint density at 1 and 1 divided by, that's the denominator, will be the marginal density for S only evaluated at 1, right? Any question? Okay, so what is the numerator from the table? What is the joint density at 1, 1? Here, right? 0.41. What's the marginal density of S at 1? 0.47. Okay, how do you get that? Oops. Sorry. Yes. Yeah, that's how we compute the marginal probability, right? The marginal density function is the summation of the joint density across R, right? So R is 0 when S is 1 plus R is 1 when S is 1, which technically you just sum over the second row, right? Which is 0.06 plus 0.41. Okay, and it gives 0.41 given 0.47 over this. And from this, we can see that actually this conditional probability is quite high, right? 41 over 47. Right? Maybe it's I think it's over 90%. Right? So this actually tells you how reliable your transmission will be. Okay? Suppose you're sending, given that you have already sent one, right? What's the chance that you're gonna still receive one? Right? This chance is pretty high. Okay, if we look at another conditional probability, zero, zero, which is the probability that given S is zero, R is also zero. Given you say you send a bit zero, you're gonna receive zero as well. What's that conditional probability? According to the definition, you're gonna divide the marginal density at zero, zero by the not marginal joint density by the marginal density of S at zero, right? So what's the numerator? What's the joint density at 0, 0? 0.45, right? So 0.45. So what's the marginal density of S at 0? Can anyone read for me? Yes, it's 0.45 plus 0.08, right? You just add the adding the first row, right? You give the marginal density, and which eventually give you 0.45 or 0.53, right? Which is also pretty high. So that means like, oh, sorry, what happens to this line again? Okay. That's how we compute the conditional probability density function. Okay. Let's see another example, which we have met before. We flip two fair coins, H, the total number of heads, and B, the binary number the two coins represent. Right? So from our previous practice, we actually have computed the joint density function, right? Is here. And also we have computed the marginal density function for both. I'm gonna just use H. So this is a FH, right? Okay, so use marginal probabilities and conditional probabilities. We can compute. We use marginal probabilities and joint densities. We can compute the conditional probabilities, right? So let us just try the condition on H. So what is the conditional density function where your B, conditional H, where B you takes say 1 and H takes 0. According to the definition, this is the joint density at 1 and 0 over the marginal density of H at 0, right? So what's the joint density of B and H at B is 1 and H is 0? What's the numerator? Just 0, right? If you look at B is 1 and H is 0, actually is here, right? So numerator is 0, right? And no matter, what is denominator is just 0. Okay, so now let us try another setting, right? So what is the say H is H is 1 and B is 2. What's the conditional probability density of B given H, where B is 2 and H is 1? Okay. So, I mean, again, we just leverage the definition, right? So we're going to divide the joint density where B is 1 and H is 2, H is 1, B is 2, H is 1, and by the marginal density of H, where H is 1, right? What's the numerator? B is 2 and H is 1. Yeah. Yeah. It's here, right? Sorry. It's here. It's 1/4, right? So what's the marginal probability that you have a marginal probability density for H, where H is 1? Y is 1/2. Yeah, sum the row, right? So the marginal probability is computed if you want to look at the marginal probability of H, right? Remember H represents rows, right? You're gonna marginalize out B. That means you're gonna sum over the values of that row, right? So that will give you 1/2. So the denominator is 1/2. So what is conditional probability? 1/2, right? Does it make sense? Any question? Okay, I mean, this is just the practice of the definition. It's a little bit mechanical, but please make sure that you totally understand the definition and know how to calculate that. Okay, so now we can introduce the independence for random variables. So remember, previously, we talked about independence between random events, right? The events are represented by sets, right? So we say if two events, A and B, are independent if and only if the following conditions are satisfied, right? I mean, all those conditions are equivalent to each other. You can use any of them, right? So we can either check the joint probability of these two events, A and B, whether it can be represented by the product of the probabilities of each individual event, P of A times P of B. Or we can check the conditional probability of A happens given B happens is the same as the marginal probability that A happens. So this basically means that the probability of A happens has nothing to do with whether B happens or not, right? Because conditional on B, the probability still the same as you don't condition on B. Or on the other way, the conditional probability of B given A is the same as the marginal probability of B, meaning that the condition A doesn't have any influence of the probability A happens or not. That's for events, right? That's not for random variables. Remember, random variables are not events. Events are represented by sets, right? Sets of outcomes in the sample space, right? But here we're talking about random variables, X and Y, right? They're mappings from samples to real world numbers or real numbers, right? So how do we define the independence between random variables? So although the meaning of the definition of the random variables and the random events are totally different, but they have like very symmetric form to define the independence. So what's that form? we define two random variables, x and y, are independent if and only if the joint density of these two random variables is the product of the marginal density for each individual random variable. And this equality must hold for every value x and y can take. Okay, so let me repeat, right? So if the joint density function of x and y is the product of the marginal density of x and the marginal density of y at every possible values of x and y can take, then we claim that x and y, these two random variables, are independent with each other. Any question regarding the definition? Everyone's comfortable? So see, actually, it's very, very similar to the, I mean, in terms of form, not the meaning, right? It's very, very similar to the definition of the events, right? When we say two events are independent, we just look at the joint probability of these two events, right? It is equal to the marginal probability of A times marginal probability of B. And here, when we switch to random variables, we just look at the joint density function, whether they are equal to the density, the marginal density function for A for X times the marginal density for Y. Okay, and then how does this definition connect to our independence definition for random events? Okay. So we want to draw some connection, right? We don't want to we don't want them to be like irrelevant. So actually, on the underlying, there is some like strong underlying connections between the two types of independence definitions, and you can show that the two random variables x, y are independent will lead to two types of random events are independent always. What does it mean, right? It means that if x and y, these two random variables, are independent to each other, then all the events defined by x are independent from all the events defined by y. So what does it mean for all the events defined by x? It means if I take a look at the event like x belongs to some sets A, and this is a type of events, right? And all the events defined by y is the event that y belongs to some set of B. And A and B are just arbitrary sets of the sample space. And this definition tells us that if the two random variables x, y are independent, then we claim that for any event A and any event B, the probability that so any set A and any set B, the probability that x belongs to A and y belongs to B is the product of the probability x belongs to A times the probability of y belongs to B. So you see there are two types of events, right? One event is that, okay, x belongs to a particular set, right? That defines one event. And the other event is y belongs to another set, right? That defines another event. And this side, A and B, can be arbitrary subset of the range of X. Okay. And then we claim that these two events are also independent with each other. Any question on understanding the point here? Okay. So you see, the independence definition for random variables says only that the events, these events like X equals to A, and the other event, Y equals to B, are independent with each other, right? Why? Because the joint density function values is actually the probability of the joint probability of two events. One event is X equals to A, the other event is Y equals to B, right? So we require that if we say X, Y are independent, it means that this joint density can be written as the marginal densities for X and Y, right? Which is just the marginal, which is probability that X equals to A times the probability of Y equals B, right? So that's how we define the independence between random variables. They're just talking about the events in the form X equals to A and Y equals to B are independent of each other, right? But now actually we can conclude that this definition extrapolates to a larger type of events. We could say, we could look at any events regarding X, meaning X belongs to a subset of values, right? Not just the X equals to a single value. If we can take arbitrary set of values that X can take, say A1 to AM, an arbitrary set of Y values, so B1 to Bn, right? So this X belongs to A and Y belongs to B are different events, right? It's not just X equals to a single value. Actually, it means X can be a subset of values, right? So these two events, we can show that as long as X, Y are independent, these two events are independent as well. So see that this is actually a very powerful definition, although it is only defined on the event that X takes a particular value. Actually, from that, you can tell any events related to X and any events related to Y are independent as well. Any question? Okay, so why is that case? So due to time limit, I don't think we are able to show this. We're gonna show why we can extrapolate the independent of X, Y to any events regarding X, Y. We just do some like a little practice from the definition. So going back to our wireless communication scenario, this is our joint probability density for S and R, right? So how do we check if R and S are independent with each other? Following definition, right? Following definition, we just want to check whether the joint density can be decomposed as the product of marginal densities, right? So here is the marginal densities. That's for R. R can take 0 and 1. What's the marginal density of R when R takes 0? You just need to, yeah, 0.51, right? You just need to add rows, right? By 1, and the second one is 0.49, right? And what is the marginal density for S? You just need to add columns, right? So for S equals to 0, you're gonna sum over the first row, which is 0.53, and second one 0.47, right? So now we just need to check for every entry in this table whether it is the same as the product of the values of the marginal PDF for R and S, right? So we can just check the first one, right? See, when S is 0 and R is 0, you know the drawing density is 0.45, right? And what's the product of the marginal densities? 0.41 times 0.43, right? Okay. This guy and this guy. Well, it's hard to say exact value, but I guess it's around 0.25, right? Of course, it's very different from 0.45. What does it mean? It means R and S, because yes, it means R and S are not independent. Why? Because if you want to see independence, you need to make sure every entry in this drawing density table is exactly the same as the product of the corresponding marginal density function values, right? As long as there's one entry doesn't satisfy this, then there's no independence conclusion. Okay, and see you after spring break. Have a great holiday break.